Today we are going to put the video generation circuit together, but before we even start I want to break some news. CAVIA has become smaller. It has shrunk. I've managed to pack the logic in a smaller package, a PLCC 44 pins instead of the original PLCC 84. There were a few things I needed to do to manage to achieve this shrinking, and that's what I'm going to explain to you now. If you recall, this is how CAVIA was originally set up. CAVIA produces an address to index the video memory where the character tokens are stored, and as an answer to that request through the data bus, CAVIA gets a character token code which roughly corresponds to the address of the first byte in the character map. And then CAVIA also constructs a character memory address to index, of course, the character memory, and that address is constructed with the 8 bits of the character code, so these are 8 bits in here, and then 3 other bits from the token line passes counter, which helps CAVIA scan each token line 16 times. And the idea of doing this, as we've discussed before, is that you have to scan each byte of the character twice in order to fill the screen, so you get 8 times 2, 16 passes. We use the 3 most significant bits of the token line passes counter as the 3 least significant bits of the character memory address. So here we have 3 bits, and this result here has 11 bits to address the 2 kilobytes here in the character memory. So that's how it normally works. The character memory replies with 1 byte of the character's bitmap at a time, which gets loaded in this shift register here, and then on each shift register clock cycle, one of these bits of the respective byte is sent out to the monitor, to the screen. That's how the whole thing works. Now, notice the following. This operation here inside CAVIA is trivial, like we discussed before. It's just wiring. We take these 8 bits and wire them up to the most significant 8 bits here, and then we add these 3 bits of the token line passes counter, append these 3 bits to the least significant bits of the character memory address. It's that simple. So in fact, we don't really need to do this within CAVIA. We can just pass these 8 bits straight there, and the result would be this. These 8 bits go straight into the respective positions of the character memory address, and then we use only 3 pins in CAVIA to pass these 3 bits here, the 3 most significant bits of the token line passes counter, and then we have the solution. So why did I do this like so before? My assumption was I need to use a fairly big CPLD for the CAVIA logic anyway, so I would have the pins available, and if I had the pins available, by wiring them through CAVIA, I would keep the possibility open for, in the future, to do some more complex processing of this address, some other strategies of addressing, and I thought, why not? But then I asked myself the question, well, if I do this instead, I will be saving 8 pins here to input this 8 bits, plus 8 pins there to output the same 8 bits to the memory, so I save at least 16 pins. Can I then fit all the CAVIA logic into a smaller PLCC 44 package instead of the original 84-pin package? Could I do that? And it turns out that I can. No margin is left. It was difficult to fit it in, but it did fit, and then the gains are just too big to ignore. It's a smaller chip, the PCB will become smaller as well, although there will be more, not more traces, but the PCB will be simpler and smaller as well. So that's what I've done. So here are the changes. I'm using a different device. Now it's a 1504. In a PLCC 44 pins package, so it's a significantly smaller device. The sole input is the CAVIA clock that is produced by SCANC, and then the outputs are now only 2. These are the 11 bits of the video memory address which addresses the 2 kilobytes of the video memory. And now I'm exposing to the outputs what was before buried logic, the line passes counter that is supposed to count the 16 passes over each character token line in video memory. I'm exposing them to the output now because the 3 most significant bits of this counter, they are used to compose the character memory address. They will be the 3 least significant bits of the character memory address. I'm exposing all 4 of them, including the least significant one, because it might be useful under certain circumstances. Now the buried states are now only 2. The token line counter, this will count over the 40 tokens per line in the video memory. When it tries to count to the 41st address, it will reset itself before it actually does that. And we need the internal states of the fallback address, such that at the end of a token line, if we need to pass over the token line again, we know where to fall back to, what is the first address of that token line. The rest is identical to what you've seen before. The logic is exactly the same, except that it ends here. There is no logic for composing the character memory address, because that will now happen at the level of the PCB, the printed circuit board. With this update done, I could proceed and put together for the first time a complete prototype of our video generation circuit. It has CAVIA sitting on a development board because I didn't have the right adapter at that time. We have SCANC with the correct breadboard adapter connected to the breadboard, and we have 2 EEPROMs playing the role of video and character memory, just to simplify the test setup. Okay, we are ready to test it. I connected the VGA cable here on this connector. I have the red input of the RGB signal wired together with the green and the blue. So this is the sole color signal. It comes from the mid terminal of this potentiometer here, which is playing for now the role of analog video circuitry. It will not work well, but it will work enough, I hope, for us to see whether the right things are on the screen. The right pin here, where the VCC usually comes, that's the color signal that comes from SCANC, and the other side is just grounded. So the color signal comes from SCANC, passes through the potentiometer and goes into the R, G and B pins of the VGA connector. Just to give you an overview of what's happening, CAVIA is on the development board because I don't have the right socket, like the right adapter like this one yet. I'll get it in a few days. SCANC is here. The clock for CAVIA comes here from SCANC. So I'm using this oscillator here, 25.175 megahertz, which is the right frequency to generate the clock for a SCANC, and SCANC in turn generates a masked clock or a CAVIA clock for CAVIA. Now these lines here are the addresses for the video memory, and I have a EEPROM playing the role of video memory, just so I don't need anything on this side here to load the video memory and the character memory. By using EEPROMs, I program in advance, I know what they have, and I simplify the whole thing for the test. The address for the character memory in here comes mostly from the video memory. It's the 8-bit output from the video memory, plus these 3 signals here, which are the most significant 3 bits of the line passes counter. We've talked about it in episode 2. And then the output of the character memory, 8 bits, go in there into SCANC. So these 2 wires here are the vertical sync and the horizontal sync that go into the VGA connector there, and the last wire into the VGA connector is just the common ground, which is connected here to the breadboard. So I've set this potentiometer at more or less middle value, so we can start testing. So at this point there is nothing more to do but to turn it on and hope for the best. There we are. Fingers crossed. 3, 2, 1. Oh, there is a sync. Yeah. There is an image. And indeed, I loaded the video memory to scan through all the character tokens, and I loaded the character memory full of all the character definitions of the ZX81, and that's what you see there, except that it's mirrored. I either did something wrong loading the character memory or something wrong here in SCANC. I reversed some order. It's no big deal. The important thing is the syncs are working, CAVIA is scanning through the video memory, and it is addressing the character memory correctly because I see all the characters there. Let's play around with the potentiometer to see what we can do. This only gets worse. Here's the image I'm actually getting. As I just mentioned, there's one obvious problem. The characters are mirrored. That's not a big deal. I know where this is coming from. I'm just loading the byte into the shift register in the wrong order. I'll explain this in a moment and we can fix it. The other problem is more difficult. The first two characters in every line are repeated. You see DD, parentheses twice, TT, 55. And one of the characters is being skipped. So if you look at the first row to the end, all the way to the right, it ends with A, B, and then the first character of the second row to the left should be C, and then D, E, F. But instead of C, we have D twice. So something is out of phase there, is out of sync. We have to look into that in more detail, which we will do shortly. The final problem is not a big deal. You see an obvious color problem. Instead of white, we are getting yellow, which sometimes goes to sort of orange, reddish. Well, the reason for that is that this prototype for now has no analog circuitry to do any signal conditioning. So all I am hoping is that I see what the circuit is trying to print. Later on, we will worry about printing it nicely and beautifully. Yeah, but now I'm at zero resistance on the potentiometer. According to the standard, the color signal should have an amplitude of 0.7 volts. And now it has an amplitude of almost 2 volts. So if I bring it to 0.7, which is about here, why is it like that? Yeah, the explanation is that my TV, which is playing the role of monitor, bizarrely expects TTL level in the RGB signal, so peak to peak of 5 volts instead of peak to peak of 0.7 volts according to the VGA standard. I know there are TVs and monitors that have these exceptions, so I simply happen to have one apparently. But we can make the circuit appropriate for all kinds of TVs and monitors just by adding a little trim potentiometer, so we can adjust the voltage level of the signal depending on the monitor or television we are using. That's not a problem. Let's go now and try to solve the two actual problems, the mirroring and the repetition of the first character of every line. Characters on the screen are always printed from left to right, like this. So if I want to print, for instance, the character O, which you see here, and I'm going to print the second byte, it will go 0, 0, 1, 1, 1, 1, 1, and then the next two zeros, always from left to right. So in the shift register, the first bit that has to come out is the most significant one, and the last bit, the least significant one. But look at what we are doing. Here there is a byte in the character memory, and with the 8 bits, and then the most significant bit is this one here. But when this byte is loaded into the shift register, the most significant bit, which is this little guy here, it will end up here. If I don't flip it around, it will end up here. And since the shift register is shifting to the right, the most significant bit will be the last one to be printed. So this guy will actually be printed in that position. And this guy, since it will be the first, it will be printed in the first position and the characters will be mirrored. That's exactly what's happening. So what I have to do to solve this is pretty obvious. When I load the byte, I have to invert it such that the most significant bit is here and the least significant bit is there, and it will be the last one to be sent to the screen. The correction of this problem is very, very simple. Here we define a field call the character byte mirrored or char byte mirrored. And in the definition of this field, we just take the character byte bits, the 8 bits, and we flip them around. And they will be loaded in this flipped around form into the shift register, and that alone will solve the problem. If you recall the logic, this is the simple logic of the shift register defined in terms of these fields, so we don't need to write this down 8 times. On the CAVIA clock, when a new character byte has to be loaded in parallel into the shift register, the inputs will be defined by those flipped around bits that you saw. So that byte will be loaded mirrored. And when we are not on the CAVIA clock, then the inputs will be defined by this shift one right field, which, if you recall here above, shift one right is this field, and then all we do is that we shift the bits one bit to the right, and we append a 0 all the way to the left. That's as simple as that. And here's the image you get. Clearly, the mirroring effect has been corrected. I'm basically mirroring the characters twice, so they cancel each other out, and we have the correct image. You see it in green because I also made another modification. I started using only the green channel of the RGB signal, because the image looks sharper, looks better, and also it's a nostalgic thing for me to see the screen in green. It's a throwback to the green phosphorus monitors of the late 70s and early 80s. So I think I will stick to the green for now. Now, there is the other problem, which is still there. The first character of every line is dropped out, and the second one is repeated instead. But if you look close to this picture along the extreme left edge of the image, you will see that there are also some spurious vertical lines there. And this, together with the character problem, suggests to me that we are having a initialization problem. The different system components, like the horizontal counter, the shift register, and the address counters in CAVIA, they do not have the correct phase relationship between them during startup, during initialization, because it's not necessarily the case that they should all start at the same time. Maybe they shouldn't. Maybe they should have a different phase relationship. So what I proceeded to do, I experimented with adding a few strategic delays to different system components, so they all start at the right time with respect to one another, with the right delay with respect to one another. For instance, CAVIA's address counter gets started just before the horizontal address counter gets started, or the shift register clock has a different phase relationship with respect to the CAVIA clock. So these are the experiments I did to correct this. Now, to get the initialization right, we have to make sure that the different parts of the system are initialized with the right phase relationship with all the other parts of the system. I will show you all the changes that I've made. I have added one internal state associated with pin 45, but not sent to the outside, that I will call go. And that will help us synchronize the phase between CAVIA and the shift register and the counters by keeping track of how many cycles have elapsed since we initialized the system. Now, the clock circuitry up to here is what you've seen before. Before, the CAVIA clock was defined by state 0000 of the clock circuitry, but now I'm taking 1 in the least significant bit. So now the CAVIA clock will tick when S0 is 1. In other words, 0001. And therefore, it will tick already on the first clock tick, the first pixel clock tick when we initialize the system. Now, go is a state defined here. It's basically a D flip-flop with its input set to 1, hardwired to 1, but that input will only be latched on the output of the flip-flop on the clock tick, and the clock will be defined by this state when S1 and S0 are 1, 1. In other words, on a count of 3 of the clock circuitry, which is composed by these 4 states here. And this will allow the horizontal counter here to start counting only on that third clock tick. And it turns out, for reasons that I understood a couple of days ago, but I don't quite remember anymore, but believe me, it works. The horizontal counter will only start counting when go becomes 1. In other words, when S1 and S0 are 1 on a count of 3. So CAVIA will get started before the horizontal counter, because the clock enable here of the horizontal counter is given by go, and that small difference in the initialization will set the phase between CAVIA and the horizontal counter, and therefore the vertical counter as well, correctly on the startup of the system. There is one more thing that I have changed, and it's all the way here. Before I had the negation of S1 as the shift register clock. Well, that doesn't work for reasons that I've explained to you right now. The challenge, if you remember, is to generate a shift register clock signal here to drive this shift register with half the frequency of the pixel clock. That was the challenge. And we approached this challenge by building a 4-bit counter which would work as a clock divider. So the idea would be, okay, if I have these 4 bits counting from S0 to S3, you see here that S0 changes state every time there is a clock tick, and the clock for this counter is the pixel clock. So S0 changes state with the same frequency as the pixel clock, and S1 in turn changes state with half the frequency of S0, as you can see here. So what I said before was, well, if we just get S1, the state of S1 for the shift register clock, then we will have half the frequency of the pixel clock. And that, of course, was wrong. Why? Because a clock signal only counts in the rising edge or the falling edge, not on both edges. Let me explain this better. If we print these signals here, the pixel clock, S0 in here and S1 in time, you see that every time the pixel clock ticks, S0 will change state. So in the first tick, S0 goes from 0 to 1. In the second tick, it goes from 1 to 0. In the third tick, again from 0 to 1, and so forth. And S1 will do the same, but with half the frequency. Now, remember, only the rising edge counts. So if I take this rising edge here of the pixel clock, at the same time there is indeed a rising edge in S1. When will we have the next rising edge of S1? Here. That's the next one. How many pixel clock ticks we will have had until that point? Well, 1, 2, 3, 4. So S1 is in fact 1/4 of the frequency of the pixel clock, if we keep in mind that only the rising edge counts, not the falling edge, and that was my mistake. The falling edge does not count. So S0 is the correct state to take, because you see there is a rising edge of the pixel clock and S0 is rising here. When is the next time S0 will rise again? It's here. How many pixel clock ticks will we have had until that point? 2. So after making all these corrections and adjustments, I reprogrammed CAVIA and SCANC, and the result was very rewarding. As you see here, the problems are gone. We still have to improve the image quality a little bit by applying some good signal conditioning with an analog circuit, but we will do this in the next episode. For now, just enjoy the nostalgia of seeing a Sinclair ZX81 character set on the screen with green phosphorus-like colors.